Are you ready? Okay. Thank you, Samir. Then I'd like to welcome everybody to this today training in mic LitPack module. Myself, I am Mads Moller. I am a senior project manager in NIRS, and I am project manager for this ICZM Egypt project we are currently undertaking in Egypt. And I am nearly at my side, at least mentally at my side, assisted by Dr. Ibrahim. Ibrahim, if you could please introduce yourself.
ثانكس مان. طبعا حضراتكم كلكم عارفين يعني مش ولا حد مش عارفني. طب الاخوه هم الدكتور سمير نفس المجموعه الاسبوع اللي فات ولا حد ثاني مختلف؟
لا في 4 أو تقريبا 4 جداد يا دكتور.
طيب اللي ما يعرفنيش انا استاذ متفرغ في معهد البحوث الشواطئ مركز قومي بحوث المياه. كنت مدير معهد الشواطئ لمده حوالي 10 سنين وبساعد المادة في إدارة هذا المشروع في مصر. يعني الإخوة معظم التيم من مصر، أنا بليد الفريق هنا في مصر. وده طبعا جزء كبير جدا من الشغل اللي احنا عايزين نعمله اللي هو التدريب. وحضراتكم طبعا ربنا يوفقكم النهارده تاخدوا اللايف 2020 LitPack وبعد كده تاخدوا فلادنج ان شاء الله ربنا يوفقكم. انا عايزين بس النهارده ربنا يعين الدكتور سمير على اليوم الطويل بتاع النهارده ده ان شاء الله وتستمتعوا مع الدكتور سمير. شكرا جزيلا وبرحب بحضراتكم جميعا. ثانكس مات.
Thank you, Ibrahim. Yeah, and then the more interesting folks, and that's the one that will entertain you for the most of the day. Dr. Samir, which I present at your side. I don't know whether you assisted with Engineer Ahmed today, Samir, but he might not show up another time.
No.
And then, okay, that's okay. And then I am assisted by my good colleague, Engineer Hendrik, who will, together with Dr. Samir, take you through today's program. And I will just start by a fairly short introduction, giving a feeling of why we are gathered here today. So, as I mentioned, we are undertaking this project ICZM Egypt, which is a coastal.
Sorry, Matt, for interrupting. I'm getting quite a heavy echo here. I don't know if that's related to audio settings in the audience.
It's most likely, but as long as you, Samir, can hear us clearly, then it's fine.
Excuse me, what is your problem? Okay, I will try to reduce the sound.
Yeah, if they can hear us, it's fine, of course. I could hardly not understand what you're saying.
Okay.
And now we cannot hear them at all. They muted themselves, but
دكتور سمير دكتور سمير خليك احسن على الصوت على بس تقفل الصوت. هو الدكتور سمير ما دوش سامعين خلاص مفيش مشكله. دكتور سمير can you hear us?
Your sound was perfect now, Mass.
It's okay, Dr. Samir.
Dr. Ibrahim?
It's okay right now, it's okay.
Okay, nice.
And you can hear us clearly?
Yes, we can hear
okay.
you.
It's actually it's better now. So let's continue. Sorry for that. So to as I mentioned, NIRS together with our partners in Egypt is currently undertaking this ICZM project, which is ICZM stands for Integrated Coastal Zone Management, and the project covers the entire 1,200 kilometers coastline, the Mediterranean coastline of Egypt. And an integrated coastal zone management is actually a methodology, or it's meant to develop a methodology to for the various institutes and ministries and authorities in Egypt to come into an agreement to how to administrate the coastal zone for the mutual benefits of everybody, instead of an independent approach where the different authorities is only looking into their own benefits. So that is the overall goal of the project. Part of this project is then to increase the technical capabilities within the various authorities, organizations, to work with all these tools that we are developing. So in order for continuing this ICZM process even after the project is concluded. And in order to do that, we are currently undertaking this technical training program, where this training in the coastal morphology modeling is part of the level 1 tool training. As you can see here, that part also consists of training in wave modeling, flood modeling, which is also Mike tools. It also consists of saltwater intrusion modeling, GIS platform training in the risk assessment model, and a training in technical training in crisis and disaster management. So that's the level 1. Selected participants of the level 1 tool trainings will then be invited to attend the level 2 super user training. Will be training in more details, more technical, and then again there will be also be training in the data management and forecast system, and even a level 3, which is the training of trainers, which is meant for people to continue this training exercise after the project is concluded. So this is the overall training program. It's just to give an idea that this specific training, the coastal morphology modeling, is part of a greater scheme of training, of improving the technical capabilities for all of you guys within the authorities and Institute of Egypt. And this specific training in coastal morphology consists of 3 sessions for this level 1. Let me just do like this. Where the first session is today, will be covering a general model setup and calibration. Then we have a session, I think it's scheduled next Monday. Then we will move more into scenario definition and statistical analysis of the modeling results. And then will be further elaborated on the third session in 2 weeks' time. And then again, you see here that the super user training, selected users will be, or selected trainees will be invited for this level 2, which consists of additional 3 days of training. And for the very day-to-day, the purpose is to give a general theoretical introduction to the sediment transport mechanisms that will again lead to shoreline changes. and then a general introduction to the LitPack modules. And by the end of the day, you should be able to tick those off, and it will be done by walking through these 4 subjects that have been mentioned, and that are again reflected in the agenda shared and shown here at the program. So yes, that is an introduction to the training, why we are gathered here today. Hopefully you will extract as much information from Dr. Samir and Hendrik as possible, because that is indeed the purpose, is to transfer the knowledge to you, so you can work independently at your own, and again transfer the knowledge you receive in this training course to your colleagues at your respective workplaces. Ibrahim, will you please take over in Arabic maybe?
Yes. Thanks ماز. الكلام اللي قاله ماز دلوقتي إن احنا عندنا 3 ليفل للتدريب. التدريب الليفل الاول اللي انتوا فيه حاليا، وده احنا بناخد فيه اللي هو خدتوا انتوا الويف موديلنج، الاخوه اللي خدوا معنا الويف موديلنج، وبعدين هناخد النهارده المايك ليت باك، وبعد كده هنشتغل على الفلاتنج. طبعا ده الليفل الاول. الليفل الثاني اللي هيستمر من حضراتكم وهيجتاز يعني المستوى اللي هو المطلوب، هيكمل معانا في الليفل 2. بعد ليفل 2 هناخد ايضا 3 ايام في الليت باك ليفل 2، وده يكون فيه ديتيلز اكتر بالنسبه. لكن المستوى الثالث اللي هو تدريب المدربين، هتبقى حضراتكم مسؤولين عن تدريب زملائكم في المؤسسات وفي المعاهد البحثيه وفي الاماكن اللي حضراتكم شغالين فيها. وبالتالي هو مهم جدا حضراتكم تعرفوا البيزكس وتعرفوا تعرفوا كل حاجه النهارده من الدكتور سمير، ربنا يوفقه. واحنا عايزينكم تكونوا ان شاء الله يعني سفراء للمشروع بعد كده، بعد نهايه المشروع. يعني المشروع كل مشاريعنا للاسف بتنتهي مع نهايه المشروع. المشروع ده المفروض ان هو لما كنا بنقول في البرزنتيشن دايما ان هو اندلس بروسيس، عمليه لا نهائيه. قضيه تنميه الساحل الشمالي من مصر وادارته عمليه غير منتهيه. بنحط خطه وبعدين بننفذها وبعدين بنقيم الخطه، بعد كده بناخد من الخطه الايجابيات ونزود عليها او نستفيد منها، ونشوف السلبيات ونحاول نحاول نتخلص منها. وبالتالي هي عمليه مستمره، وده خاص بالمشروع، مشروع للاداره وليس للتنميه. وبالتالي كيفيه اداره الريسورسز اللي موجوده عندنا في شمال مصر كله، من رفح لغايه سلوم 1200 كيلو. فالموضوع مهم جدا لحضراتكم وللبلد لمصر. وكومبوننت التدريب مهمه جدا، ده اللي الناس فعلا تستفيد منه. يعني احنا التدريب كلها تكون موجوده تحت اذن حضراتكم كلكم جميعا، والمؤسسات ايضا والهيئات والمعاهد، وهتبقى في مركز المعلومات اللي هيتعمل بعد كده، اللي هيتعمل في الوزاره ايضا، وزاره الموارد المائيه والري. لكن مش المهم بقى ان التقارير تكون موجوده، المهم ان احنا نعرف كيفيه عمل هذه التقارير، التولز اللي احنا شغالين عليها دلوقتي. وده احد التولز النهارده احنا بنتكلم فيها على الليت باك. الاسابيع اللي فاتوا و5 اسابيع اللي فاتوا كنا شغالين على الويب موديلنج، دلوقتي هنشتغل الليت باك 3 اسابيع، بعد كده نشتغل على الفلاتنج اعتقد 4 اسابيع. فالموضوع مهم جدا ان احنا نعرف التول ازاي نعمل، مش ازاي نقرا. التقرير تكون موجوده، لكن المهم ان احنا نعرف ازاي. وربنا يوفقكم ان شاء الله النهارده، واتمنى لكم كل توفيق مع الدكتور سمير، ربنا يعينه ووفقه. ومع انريك كمان هيكون معانا من الدنمارك لمده حوالي ساعه ونص، فحاولوا تفهموا منهم ان شاء الله، وربنا يوفقكم. شكرا جزيلا. Thanks, Matt.
Thank you very much, Dr. Ibrahim. And I think we'll just move on to the fun part of the day today. So I will not take any more of your time and give the work to my good colleague, Engineer Hendrik. So please take over, Hendrik. Maybe you could start by introducing us, making a short introduction of yourself.
Yes, I was also thinking that. Thank you, Mads. I'll start by sharing my screen. Please confirm that you can hear me okay and that you can see a cursor on the screen. Then we have the in the audience, Samir, then we have the technical side of things sorted.
الصوت كويس دكتور سمير. Can you hear this?
Everything is okay. Go ahead and.
Great, thanks. Yeah, I'm Matt's colleague, and I'm also based in Denmark, working for NIRAS, a coastal and offshore engineer. I'm by trade civil engineer, and then my master in coastal engineering and water and environment. Throughout my career, I then shifted a little bit to the offshore world. Most of the offshore world did a lot of offshore spectral wave and hydrodynamic modeling, met-ocean analysis, and now with NIRAS moving back to the coast. But I guess I do really like this, the interdisciplinary work, and as we also will see here through the next few days, it is crucial to keep these things in mind. The input parameters to the LitPack modeling and to the coastline evolution, they are very, very crucial. So having a good interdisciplinary mindset and understanding all the parameters involved, that's from experience, that's a good idea. So what I'm doing today here is the sort of first 1.5 hours I think we settled on. We see how we go with the time, is to give a short introduction as it reads here in the agenda on the slide, short introduction to sediment transport and morphological processes. Why does it not react now? Okay, I need to use the keyboard. So the program that I set out for my part are just some general coastal terms. And then point 2 to 4 will actually be hydrodynamical processes along the coast, the nearshore wave process, the nearshore currents, and the water levels. Because as we will see, these are governing the littoral transport, of course. So a large part of the littoral modeling is actually concerned with describing the hydrodynamic conditions along the profile and along the coast correctly. And then the last part is to then from that derive the sediment transport and analyze the morphological processes. The last section, a few references. The slides will of course be distributed at the end, so the references are for you also. A lot of it is publicly available, so you can follow it up. And the main reference of this presentation I wanted to put here, it's a freely available ebook from DHI, Shoreline Management Guidelines, and that's it's actually quite a heavy book. It's almost 500 pages, but it's really a great tool to provide engineers and also authorities and all sorts of different people a good overview, a common point of reference, a common terminology, so that I found to be a good guide and a good starting point, and then to from here find further reading and further references. But let's get into it. So coastal terms. Again, throughout the presentation, you will find a lot the reference to that what I just presented, and I also tried actually to sort of follow a little bit the structure as it is in that book, because I found it very appealing and it made good sense to me. And then I thought if you later want to follow it up again, it also makes it easier for you. So if you look at a typical coastal profile, where we have the offshore zone to the left and the coastal hinterland to the right, we have a lot of terms here. Let's look at a few specific ones. So these three here on the left are short terms for different water levels. So the mean sea level, the mean high water level, and the mean low water level. And these will, without waves, etc., will at the be placed on different positions on the so-called beach face. And the highest one of them, the mean high water level, is actually defined as the shoreline. Here, the dashed line. The shoreline, in common terms, when we talk about the coastline, we sort of often think actually about the coastline as the interface between water and and the beach. But now when we really want to be technically correct in coastal terms, that's actually not 100% correct, because the coastline is a little bit longer and actually defines the line where the morphology clearly changes. So where, for example, a sandy beach changes into dunes as depicted here. So where vegetation starts. In other places that can be rocks, it can be cliff feeds, etc. So the coastline is clearly defined. The shoreline is actually quite difficult to define as it changes all the time, depending on the water level. But shoreline and coastline are two important terms. The area between the shoreline and on the offshore side, then the area to where the I actually have that on the next slide, to where the waves start to break. It's called the breaker or surf zone. So here marked in red. So that's basically the zone of the nearshore zone that is exposed to depth limited breaking of the waves that arrive at the shore. And the outer limit is the so-called breaker line. And anyone who has been standing on the beach has observed that. So it's clearly when you see it, when you stand on the beach and look out offshore, you can a little bit offshore clearly see where the white foam appears, and that's the breaker line. But that then also means that the instantaneous width of the surf zone, so how far offshore this breaker line actually is from the shore, that varies all the time depending on the wave conditions, depending on the water level, etc., because the wave breaking is depth dependent. So where these wave breaks, that changes all the time. One definition is that we define the breaker zone as the zone where the waves associated with the significant wave height that are exceeded 12 hours per year. So it's a statistical description. If you take the offshore conditions and you take this HS 12 hours per year, then you get like sort of an average breaker zone. The breaker zone is slightly narrower than the so-called littoral zone, where littoral transport processes take place, and that's a zone that we are very interested in, of course, in the next few days of this training. 80 to 90% of the yearly littoral transport take place within the breaker zone. So we already sort of defined what we're trying to model here, but again, it is not easily defined how long offshore that actually goes. And that is also one engineer exercise in setting up these models to choose how long offshore do I need to go with my profiles, what type of offshore wave conditions do I have available, to what extent are they useful, etc., etc. We will get back to that when we set up models. So, but one consideration is to the modeling engineer, how far offshore does that littoral zone actually go? Where are the transport processes happening? What do I need to include in my model? And there are different checks also. There are small sensitivity checks that can be done when setting up the model, and you will hear that also again at a later stage. But for an initial assessment, for example, when you, I don't know, write a proposal or need to get a first idea of the modeling exercise, there are some empirical formulations which are also presented later available to get a first idea where this littoral zone extends. Let's move over to the hydrodynamic processes in the near shore area. The first one are the wave processes. I started with the wave processes because, as we will also see, they are the most important in most scenarios, the most important processes that drive the transport. So a few general words on the waves. As I said, often they are the most important factor. So having good wave data at hand is really a very crucial step in setting up a useful LitPack model. The sea state is composed of wind sea and swell waves. The swell waves are in oceanography defined where the phase speed of the propagating wave is larger than the local wind speed. So these waves are not affected by the local wind, and the wind sea waves are then where the phase speed is less than the local wind speed, which means they are affected by the local winds. In more engineering terms, you can also think of swell as generated by wind fields far away from the area of interest and are not associated with the local wind conditions. So that highlights again, I put that here. There's a very nice example here, a picture on the right, where we can see a very light swell underlying here, almost normal to the shoreline, and then from the east there is wind generated monsoon waves. And both waves, because the swell waves are actually those that are breaking, they are very important for the swell is often most important for during moderate conditions for the transport processes at the shore. It is really important to have a sophisticated wave data. So just having local wind measurements and using some empirical formulations for the fetch and wave growth and some sort of making some estimates of the wave conditions along the shore is often not sufficient, because the swell would not be properly covered necessarily. The offshore wave conditions are irregular waves, and some of you might have seen this in a bit more detail for the SW modeling, but I'm not sure about that. But I just repeat a few things here to get the context. So real offshore conditions, I called it, are irregular waves. We can statistically describe the sea surface elevation by linear wave theory in deep water and superposition of wave components, as is sort of here depicted. And then if we are in one point in space and time, we have something that's called the two-dimensional wave spectrum. So that's the distribution of energy, or sea surface variance density, which is proportional to the wave energy, distributed over frequencies and directions. So it basically says how much energy moves at what frequency in what direction. And that's good to keep in mind for what we are looking at now in the further slides. Then the wave spectra and integral parameters. We often are looking at the one-dimensional frequency spectrum, which I depicted here, where, for example, the Johnswap or Pearson-Moskowitz spectrum also exists as parameterizations of that 1D spectrum. But the 1D frequency spectrum, and then furthermore integral parameters, which you're all familiar with, I suppose, the significant wave height, the mean wave direction, the peak frequency, the directional spreading, they are all, I called it here, aggregations of the real offshore wave conditions. And whenever I aggregate something, I lose information, right? It's only approximations. And these have to be to then still come up with correct transport rates for offshore conditions. That has to be also included and is included in the LitPack model with different approximations. We will hear that again, how irregular waves are handled. Here we looked at in the slide before, we looked at the integration of the 2D spectrum to the frequency domain, and the same can be done at a given frequency in the direction. And the directional spreading, how the a commonly model that's also used in the LitPack is the so-called cosine 2S model. So it's a description that's depicted here, depending on the parameter S, where I simply said, okay, the energy at the main direction is distributed over the directions depending on the coefficient S. For small s, we have this curve here at the bottom. that means the energy at that frequency is widely spread, almost from -180 to 180 degrees. So it's a highly short-crested sea state, very confused sea state. And high S means that it's a very peaked, so not so much directional spreading, meaning swell conditions, long waves, long crested waves. And that is reduced to that is related to a reduction of the radiation stress, which I will introduce later and get back to later. Which because we can I think it's common sense when the wave energy approaching the beach is not aligned but goes into all sorts of different directions, there will be some transport associated to those wave components also be happening in all sorts of different directions, meaning that during those conditions, the net transport along the coast we would expect to be reduced compared to all wave energy being working in the same direction. Then the nearshore wave processes. When we come from the offshore wave conditions, which we sort of discussed in the previous 4 slides, where we in deep water, where the waves can perfectly oscillate, as shown here in the left, at the shore, and we already discussed that we're concerned with the littoral zone all the way up to the shoreline. So we are obviously in intermediate and very shallow water. These oscillations cannot fully develop at the bottom anymore. So that means that the depth in relation to the wavelength is having an input on the wave kinematics. And we are not having circles anymore. It starts near the bottom, but in very shallow water, it goes all the way to the surface. So we don't have these perfect circles anymore. And that means that we need to deal with nonlinear theory, wave theory, which is important in shallow water to resolve the high order aspects of these waves, which are very important for the sediment transport. Unfortunately, no universal theory exists today which is applicable in all conditions. And that's also the reason why different nonlinear theories are available and can be selected by the user in the different components of the LitPack model. And one common, and it's an engineering choice to which wave theory is applicable. There are some semi-empirical formulations also available in the LitPack. They sort of try to cover a wide range, but a commonly one and also in some DNV standards presented is this diagram here shown to the right, where for different conditions the applicability of the different non-linear wave theories is shown, which with also the sector down here for the linear wave theory. Then nearshore, the waves then are undergoing different transformation processes, and the ones due to the shallow water are the changes of wave conditions with water level variation. And that is in that bullet point is meant that while offshore, it's not relevant that the still water level position because the water we are in deep water anyways. Along the coast, the high tide or low tide or storm surge or not storm surge allows waves with a certain wavelength to propagate further to the beach without breaking. So where the break, we already heard that in the beginning, where the breaker line lies and how the wave breaking happens on the beach depends on changes in the still water level. We have the shoaling, the refraction, the bottom friction, the breaking, the setup or set down, which I will cover in the seawater level part later, and the swash, uprush, and the run up. And this is from an old university lecture script, a picture I really like that sort of depicting all these different processes. We're looking at a few now closer. So the wave shoaling, that's the change of the local wave height as the waves approach the foreshore due to the changes of the wave propagation in shallow water, which is sort of shown in the picture down here. One can introduce a shoaling coefficient Ks, which is the ratio of the local wave height over the offshore wave height. And by the way, here now we're looking at individual waves, right? We are away from the irregular waves, a significant wave height spectrum, etc. Now, for the nonlinear theory, we're looking at individual waves, and we will later again see, okay, how do we now handle, how do we close the gap between the offshore 2D spectra and now nonlinear theory of individual waves. So we have that ratio Ks between the local wave height H and the offshore wave height HO. So not HMO, but just the offshore wave height HO. And that graph is shown here, which can be computed with the with wave theory. And what we can see here, once the water depth is hitting is about 50% of the wavelength, so that's here at 0.5. We have Ks. Until then, we have Ks1. So it happens. It starts to happen. Shoaling starts to happen approximately at 50% of the offshore wavelength. And then first we have an initial reduction of the wave height to about 0.9 or 90% of the offshore wave height. And afterwards we have a steady and huge increase of the local wave height. But the increase that is shown here is close to the beach, of course, limited by wave breaking. So we won't see like a shoaling that can develop up to 2.6. That was the shoaling. The wave refraction is the there's a depth refraction, which is the turning of the wave propagation when at angle with the depth contours. And that's again related to the phase velocity in dependency on the water depth. So that a part, when we now look at the wave crests, a part of these, the nearshore part of the waves is hitting the shallower water and thereby slowing down, whereas the offshore part still travels at the higher velocity, and thereby tend the wave crests to align with the contours, and which in our context now, where we're looking at sort of beaches which parallel contours, that means they are also aligning with the beaches as it's depicted here. Like the contours are of course not everywhere parallel to the beach. The depth refraction is for our application the most relevant one, but just for completion, currents can also refract waves because the phase velocity is also affected, of course, by the current speed of the ambient water column the wave is propagating through. And then we have the wave breaking. We already heard it. It's limiting the shoaling at the beach. And as a rule of thumb, the wave breaking starts to occur roughly at a wave height of 0.8 times the water depth. So that's where, if you have a given wave height, you can position the breaker line offshore based on that condition and looking at the contours. Rule of thumb. There are three waves of breaking. Three modes of breaking. The one is the spilling. So on very flat shore faces, we have that here on the top, where sort of the gradually over the length of multiple wave lengths, just the top of the wave sort of drizzles down. If there are surfers, as you can also see here in the pictures, they would call that a beach break. So it's a very mild break and very, very popular for beginner surfers because you can without you're not exposed to a lot of energy. The energy is dissipated quite gradually. Yeah, as I said, it's happening over a fairly long distance. Then the second mode is the plunging, and that's on moderately steep shore faces. So where the slope is a bit steeper, and here the upper part of the break simply becomes faster than the lower part and breaks. It breaks over its lower part, and that's generating these sort of barrels. Again, the surfers would call the second type a point break. So this can be often seen if there's some feature in the bathymetry, and that's more for advanced surfers. And then the last one is the surging, when there's very, very steep shore faces. So where simply the lower part of the wave runs up the shore face and retrieves again. There are some areas in the world, in Iceland is, for example, a famous beach where a lot of warning signs have been put up because these sudden surges up the beach and slowing down, and then on the way back speeding up again can easily grab people that are on the beach. So yeah. Then the nearshore wave processes the wave radiation stress tensor. I mentioned it once before that the radiation stress will be impacted by the directional spreading. We look at that again. But first, the stress tensor itself. If we consider unidirectional regular waves as depicted here, which are propagating in the direction x1 and the orthogonal direction is x2. Then there will be stresses associated in the 1-1 direction, that's the S11, and in the x2 direction is the S22. So that's a typical engineering way of writing it. These are the normal stresses in that x1, x2 coordinate system, and due to symmetry in that coordinate system, there are no shear stresses. So we're only pulling or pushing a little square of water. And the radiation stresses consist of an isotropic contribution, the pressure contribution, which is the excess pressure in the waves, and then the momentum part. The pressure one, isotropic, that appears in both terms, in the S11 and S22, so it's in that direction and also orthogonal to the wave propagation. Then the momentum part, it's quite natural that only occurs in the direction of wave propagation, so it's the S11, these two terms here. And now there's already an angle alpha depicted here, and that's the misalignment of the wave propagation with the shore normal. So the shore normal here would be the x and the y. And some of you might be familiar with that. If you change the let me go one second back. If you rotate your reference coordinate system and look at the stresses acting on a small control volume, in the principal directions, as said before, you only have normal stresses, but once you rotate it, you will introduce shear stresses, so that are shearing on the faces of such a control volume. And one way of figuring those out is, for example, the Moore circle that was quite popular in the times where we didn't have computers. So when you have normal stress components S11 and S22, and you rotate it by alpha, then you can at 2 alpha read off these so-called shear stresses. And these shear radiation stresses are the ones that actually drive the longshore currents. And that's the that's basically the most, in most of the cases, the most important process for the littoral drift. These longshore currents generated by the shear stresses of the waves. And it's a little bit of a long connection: offshore wave conditions, nearshore wave conditions, wave transformation, shear stresses, longshore wave currents. But we basically have to get that whole connection as good as possible to get a good description or a good estimate of the littoral transport. The shear stress component of the radiation stress decreases towards the shoreline, and that is simply because of the wave breaking. So energy is dissipated. So offshore, where no waves are broken, these stresses are the largest. As we go to the shore, energy is dissipated, these stresses decrease. And that means there's an imbalance in the shear radiation stress, and that must be compensated through a current which then has a bed shear stress with the bottom, which is counteracting and making the force balance. Sorry, one more comment on that, and we will get back to that when we later look at the littoral transport associated with these longshore currents. But I can already mention now that they are most strong where we have where the breaker line is, because there is the most energy is dissipated, and that means this gradient of shear stresses is the largest, and that's also where the largest longshore current is generated. Now back to the irregular waves. We now went through these shallow water transformation of waves, the nonlinear theories, the shear stress for one regular wave train. But we also said that we have offshore, the offshore wave conditions are a description of irregular waves. And these are also, and the integral parameters of these irregular waves, the significant wave height, or namely actually for the LitPack, the root mean square wave height, the mean wave direction, and the peak frequency and the directional spreading, they are input to the LitPack model. And internally in the model, there are two ways available how to then handle the irregular waves and translate that into a set of individual waves which can be used with the model equations. And the one is a Rayleigh wave height approach. So there we use the Rayleigh distribution, which is an expression as a function of the root mean square wave height, how the individual wave heights are distributed, and this the Rayleigh distribution is depicted here. And then in the model, individual wave trains of that Rayleigh distribution. So let's say it's a numerical model, so it's discretized. So that means maybe one here, one here, one here, one here, one here, etc. So multiple individual wave trains will be actually modeled in the LitPack model with the transformation, the braking, the shear stress, the currents, the transport, etc., and then superimposed. And the second approach is the a model based on Betjes and Janssen, which is the modeling of the local mean rate of energy dissipation. And we might get back to that later when we look at the individual model components. And at that position, maybe a general comment: you might have noticed that in this introduction, I'm presenting a lot of concepts, but not too many equations. Which the idea is that we will, as we go through the models, model descriptions, we can then have a look at how these different processes are actually handled in the models, and we can then introduce and present some respective equations where helpful, how these processes are actually handled. And now back to the directional spreading one more time. We now, with the Rayleigh wave height and the model based by Betjes and Janssen, figured out how how are now wave heights, the irregular waves handled, that the different waves have different frequencies. But the other component of it, as we saw with the offshore wave conditions, is that the waves are not perfectly aligned. We're only looking at a mean wave direction, but the actual wave direction, we have that directional spreading. And that actually, a reduction factor can be derived as a function of S. So S was that directional spreading coefficient that I presented earlier. And as we remember, for a low S, so here on the left with 1, we have a wide spreading of the energy in a lot of directions. And for a high S, we have a very narrow spectrum, and all wave energy is going in one direction. So for very narrow spreading, this reduction factor of the shear stress approaches 1. So we have no reduction, and the other extreme is the spreading coefficient of 1, which was spreading of almost 180 degrees. This reduction tends to 0. So that means if we really have a complete confused sea state, as we said before, these shear stresses of the different wave trains, they will balance themselves, because the one goes in that direction, the other goes in the other direction. So in that extreme case of having a very confused sea, we don't have the need of a littoral drift current to develop to balance the shear stress, because the shear stresses of the different wave components balance themselves. So this is a reduction factor as a function of the wave spreading, a reduction factor of the shear radiation, wave radiation shear stress, and thereby a reduction also of the littoral drift current. Now we are closing the wave section and looking at the currents, although as you will see, it's not easy to put the processes exactly into one bin, because we already looked at the wave introduced currents, so they appear both in the waves as well as in the current section. But when we now look at the nearshore currents, we have these 5 general types of currents. So the tidal currents, which are relevant, which might be relevant in the nearshore zone. So the tidal currents is as the tidal wave meets the coast and interacts with the coast, it can increase currents, which especially can be quite large in straits and openings and inlets. We have the storm surge currents, so that's irregular currents associated with meteorological events. Then we have the longshore currents. We already discussed them. These are the waves interacting with the coast are creating these longshore currents. And then we also have shore normal currents. So they are perpendicular to the shoreline, which are also generated by the waves. And then further, but that's a little bit outside the scope for the LitPack models. Only the coastal model, as you will learn later, is having some formulations to handle some of those. But when generally for the LitPack is applicable for continuous coastlines, or where at least the coastline can be put into sections that are characterized by contours parallel to the shoreline. And at these coasts, the top 4 currents are the dominating ones. But when the coastline becomes very complicated, so we have a lot of peninsulas and bays, etc., or largely varying bathymetry changes due to geological features, then we have so-called 2D currents, and these 2D currents they can only be handled with two-dimensional hydrodynamic models, and if these become too dominating, then we might be outside the applicability of the LitPack model. So we will be focusing on the top 4 currents in the context of this course for the time being. So the tidal currents and storm surges, as I said before, tidal currents are generated by the movement of the tidal wave around the Earth. I assume you're all familiar with the tidal currents. And then near the coast, the tidal wave interacts with the lands. And currents parallel to shore or through straits and inlets are generated. And currents through straits, for example, barrier islands, can cause very high currents. So they are very important for the morphological process. And that can also be that the barrier islands or other features, while your shoreline, the stretch of the shoreline that you are analyzing is fulfilling the requirement that it doesn't have any complicated features within the area of influence for your hydrodynamic conditions. You can have such features like huge harbors or barrier islands, as mentioned here. So again, it's important to have the input data available to your LitPack modeling that is accounting for these conditions at hand. So if the currents through straits or also the storm surges are relevant, it must be included in the current inputs that you're using for your model. So, and the storm surges are generated by a combined effect of wind shear stress, barometric pressure gradients, and combined with tidal currents, which is that a storm surge can have a very different effect at a high tide than at a low tide. So that should be taken into account when doing statistical analysis of high water level events and storm surges. That storm surges are an irregular occurrence that can happen at any point in time, whereas tidals are harmonic and predictable. And if you have a storm surge or a high water level in historical data, if that storm or a similar storm reoccurs, it is not given that it happens with the same tidal water level. So if a historical storm occurred during a low tidal water, the same storm during high tidal water can have very different consequences. So that's important also to keep in mind when dealing with historical data and when defining your design cases for your LitPack model. The wave-generated longshore currents, we already discussed the concept of the radiation shear stress, which are generating these longshore currents. And again, these are the dominant nearshore currents. So mainly shore parallel shear stress component of the wave radiation stress is generating these currents, as we already discussed. And there's also a little bit of surplus water that's carried across the breaker zone in form of mass transport, which also goes into these longshore currents. And as I mentioned before, these currents are maximum close to the breaker line. And as we said before, the breaker line is also not a fixed point in the surf zone, because it depends on the wave conditions and water level conditions how this wave breaking is distributed. That also means as the wave breaking position of the wave breaking moves in and out over time, that also means that the distribution of the longshore currents and where the maximum longshore current is positioned is moving in and out in the surf zone. And then we have not only the longshore currents, but also the wave-generated normal currents, which are directed perpendicular to the shoreline. And that can be rip currents, which is local currents diverted away from the shore. And that's the so-called rip gap in the bar The bar is a feature, a bathymetry feature, which develops parallel to the shoreline. And at the lowest point in the bathymetry, it's sort of where then these long shore currents meet the lowest point of resistance, one can say. These rip currents can develop, and they are also in the coastal management quite well known, because they, besides of transporting material offshore, which can be lost from the littoral process, they are also great danger for swimmers. So they are usually quite well communicated, the existence of these rip currents. And then we have the other normal currents are the mass transport or wave drift. So water particles near the surface in the wave motion are propagated towards the shore, and also the surface or roller drift. We discussed the first mode of wave breaking, where sort of steadily the top of the wave dribbles down as whitewash. These are also leading to mass transport towards the shore. And all this mass transport towards the shore needs to be compensated. So one way of compensating it are the local rip currents, but another way of compensating is the so-called undertow. So that's a compensating return flow for the above two. And anyone who is sort of be standing in shallow water along the beach in gentle waves might be familiar to that sort of with following every waves, you sort of feel at the feet a small current pulling you offshore, which is the so-called undertow. And that undertow is actually important for the formation of the so-called bars. So these sandbanks, the more shallow areas as you go a little bit offshore. These were the normal currents generated by waves. And then, as I said before, there are these 2D currents in the nearshore zone. So if we have more complicated coastlines, which clearly don't qualify for a continuous stretch of coastline, this example here, right? I have some harbor position and actually an alternative layout of that port. Then we get complex so-called 2D currents. In this example, it's a recirculation of the longitudinal current along the beach. There's a feature, we all know this recirculation, and in this alternative design, this recirculation current is actually reduced. And these have local, quite complex processes of sedimentation. In the profile, you will hear that again in the profile model of the LitPack. So where we model the littoral transport across a cross-shore profile, features like this may not be present. So a cross-shore profile is only valid for a so-called cell where the beach is continuous. But one can place multiple cross-sectional profiles at different sections of the beach where that is applicable. And then in the final module of the modeling package, of the LitPack modeling package, the littoral transports of all these different cross-shore profiles can be put into the coastal evolution model. And within the coastal evolution model, there is some empirical description or some parameterizations available to deal with some of these non-continuities along the coast, like breakwaters, etc. But there is a limit to it. So that's another responsibility of the modeling engineer to judge if this LitPack package can be applied or if the conditions and the bathymetry at the coast become too complicated and these 2D currents are too dominant, and then another model must be applied. So we're not further discussing these 2D currents here. And then the last hydrodynamical process component is the water level. Again, it's all a little bit overlapping, right? We already discussed some water level effects due to waves. So it's in the way currents, waves, water level. It's just a way how we engineers deal with the complicated sea that we're trying to put things into buckets, which has proven to be quite a useful tool. But then you realize often that there are these overlaps, of course. So variations in water levels, again, like for the currents, because it's of course driven by the same physical, or it has the same physical origin. There's the tides, which are regularly oscillations with periods from days to a year, and then are non-regular variations in water level with reoccurrence periods here on average, because non-regular, from days to several years, such as storm surge, wind setup, barometric pressure variation, seasonal variation, and climate change. Seasonal variations you have at some coasts where you have, for example, the monsoon period. So like for the monsoon periods of 3 months, you have a dominating prevailing wind direction from the one direction, and then to the north during the non-monsoon, you have the prevailing wind from another direction. And these prevailing winds, due to the wind setup, can indeed lead to seasonality of the water level. If there are these water level variations at the place you're analyzing, which cannot be positively correlated with your wave height, then which is often the case, that high winds and a large water level set up during storm surge has a positive correlation with your wave heights. Then you can often neglect the contributions or deal with that in a design parameter way that you assume a constant water level for given waves, and then you can deal with your offshore conditions in a statistical sense. So you can, and we will discuss that again in the context of scatter tables. Then you can simply say, okay, this and this wave height from this and this direction occurs. This and this has this and this probability. However, if that's not the case, so if you're looking at an area where there is no clear correlations between waves and currents and water levels, then you might have to model your littoral drift also in a historical sense, in a time domain sense, so that you, for example, model 10 years, that you have 10 years of hindcast of waves, currents, and water levels, and you model 10 years of the littoral drift, and then based on that, you can analyze your output. So that's important to keep in mind when choosing what hydrodynamic components are to be included, and what is the statistic character of those. The wave setup. We already heard about that in the waves, but to just go a little bit more into detail here, the wave setup is the increase of water level within the surf zone as a local effect, and it's due to the transfer of wave-related momentum to the water column during the wave breaking. So it's basically just pushing the water towards the shoreline. And we have the design still, and I put a design here in brackets, still water level, because of exactly that argument that I made before. Like if we have very constant water levels or clear correlation with the wave conditions, we might define as a design still water level. So we don't have a time series of it, but for the different model runs, we have a design water level, and that would then be the tide and the surge that we're considering, plus potentially the sea level rise, which you of course have all been concerned with. And that is then the so-called still water level. That's the line here. So that is the water level elevation without any impact by waves. And then we have the wave setup. So that would be the so-called flooding level at the position on the beach of that water line is the flooding level. So that is the still water level plus this wave setup, which increases towards the shore. And then on top of that, we have the wave run-up. So the periodic run-up of waves along the beach and then the run-down. So the wave impact limit, the high limit of that would be the flooding level plus the wave impact level. And that means that in normal conditions or during storm conditions, this is all the way up to here is where the beach is affected by the sea. And that of course means where the discussions or the assessments what now climate change will be doing, if then in your design still water level, if that moves up, then everything moves further up the shore. This was the water levels, and then with that the sort of run through the hydrodynamic processes that are relevant for the littoral transport modeling is closed. And as I said before, I followed quite a lot, and I took a lot of pictures, as you can find for yourself if you're interested, from that shore line management handbook. And I can really only recommend to use that also as a further reading guide if you want to review these hydrodynamic processes. And I can only iterate again, having a good understanding of the hydrodynamic processes and which ones are relevant or not, and making the right model choices, that is almost the most important step in this littoral modeling, because the input, the quality of your input data really decides on your results. And we will see that a little bit more now in this last section, and I will comment on that again. And this last section is now, okay, how do then these hydrodynamic processes, which are now propagated from offshore across the cross-shore profile, how do they transport sediment, and what morphological processes are related to it? Do we need to have a short break before I take the last 20 minutes, half an hour, or how's the audience feel? Okay, I assume you can hear me and see everything. If I don't hear otherwise, okay, I see you nodding. So as I said, last half an hour on the sediment transport itself, and I hope I didn't surprise you or bore you too much the first 1 hour with the hydrodynamic conditions. You might have entered the room here in the morning and wondered why am I talking so much about waves and currents and water levels. We wanted to model sediment transport, but I hope it becomes it now in this final section quite clear how this fundamental understanding and good description of the hydrodynamic processes is actually the fundamental part of the littoral modeling, and what huge impact that has on the results that we get in terms of sediment transport and morphological processes. So, sorry, somehow I can only use the arrows to go to the next slide, not the mouse. I'm not sure why that is. Anyhow, so a few general words on the sediment transport. The littoral transport processes, as I said, the above discussed hydrodynamic processes will result in the movement of and transport of sediment. And there are two types of transport related to the stability of the beach profile or multiple beach profiles. That's the littoral transport or longshore transport, and it's a cross-shore transport, which, of course, as you will imagine, are related respectively to the longshore currents and the normal cross-shore currents. If you have a gradient in the littoral drift, so the transport parallel to the shore, if you have a gradient, which means you have a change in that transport, you will get morphological changes. That means coastal erosion or sand accumulation, right? It's just a simple mass balance or conservation of mass. If you in a given point have more material arriving than leaving, you will have an accumulation, and the other way around, you will have a coastal erosion. So that means by understanding the littoral transport rates in multiple cross-shore profiles and then comparing them, we can get an understanding of the transport along the shoreline and also in the morphological changes of that shoreline. And that's basically where it all will come together in the very end in the coastal evolution module of the LitPack modeling. That's one way of using it. In many engineering applications, you can actually also do these some calculations and assessments yourself simply by doing a LitPack coastal profile simulation in multiple locations along the shoreline, and then compare these littoral transport rates. You get an idea in what direction the net transport are and these gradients. But we will see these applications in the coming days, also with hands-on examples. Other items. So one cause for morphological changes are these gradients in the littoral drift, and then other items impacting on the morphology are breakwaters, which can trap sand upstream in the sense of the direction of the littoral transport, and downstream erosion. And by the way, this can be different from one storm to the other. If you examine historical satellite images of some coastal stretches where you have breakwaters, you can see at the same locations the sand being trapped and eroded on both sides of the. In some locations on both sides of the breakwater, changing depending on the storm events. Then you have other coastal sections where the net transport is always in the one direction and also historically has been. So you will have the erosion and sand trapping always on the same side of the structure. Then revetments that are fixes of the coast, but of the coastline, and now recall the technical sense of coastline, which was the transition between beach and dunes, for example. So if you fix that, the beach itself will continue to erode. Then you can have other coastal structures, offshore structures, and sources and sinks. Sources and sinks can be natural river outlets, etc., or they can also be human-made. But no further details on that. These sort of punctual non-continuities, one can say, are partly handled in the coastline evolution module. But in the first parts, where we're considering the littoral transport and coastal profiles, we're mainly concerned with the littoral transport and the cross-shore transport. So the littoral transport, which is also called longshore transport or littoral drift, whereas littoral processes And littoral zone does cover both the normal and the longshore. So it's, you need to, when you read, you need to be aware of the context. It can be sometimes a bit confusing. But we're now looking at the longshore transport parallel to the shore here. It's the transport of non-cohesive sediment in the littoral zone. So that technically means mainly sand. If you have finer materials like clay-like, then this is not applicable anymore. Or the other extreme would be rocks, which are not moved, and we use them therefore also for coastal structures like breakwater. So we're looking at the non-cohesive sediments, i.e. sand. And it's mainly, as we already said, due to the action of breaking waves, and we discussed the whole causality here. And the turbulence associated with the wave breaking causes some sediment to come into suspension. And any one of us who's been taking a walk along the beach has observed this phenomenon, right? There's waves breaking along the beach. The turbulence brings sand into suspension, and actually very close to the shore, where we usually stand when we go for a walk on the beach. The sand is kind of distributed in the whole water column, but that is just because it is very shallow. The moment you move a little bit offshore, as a surfer or as a swimmer, maybe you will see that the sediment that has comes into suspension is happening quite close to the bottom, which is simply because of the high falling or settling velocity of the sand. So it's a very instantaneous response of the sand suspension to the turbulence of the waves. If the turbulence of the wave is not present anymore, and the wave breaking doesn't happen all the time, right? There's a wave breaking, and then the next time it might be in a slightly other location, the sand also settles again. Or likewise, if there's any structure, breakwater, etc., which is sheltering from the waves, there is kind of an immediate response and a settling of sand associated with that. So still, the longshore current transports sediment in two modes. So the littoral drift is the suspended transport and the bed load. And these are two actually outputs that are available from the LitPack models, as you will see later. The suspended transport is just the sum of all sediment that is present anywhere in the water column. We are not, when we're assessing the coastal evolution and morphology, we're not so concerned with in what part of the water column it actually is. As long as the underlying model is taking correctly care of that, we are happy. And yeah, as I said before, also the bed load is really transport of the bed, so sand, etc., rolling over the bed without going into suspension, but also the suspended transport happens very close to the bed due to the high falling velocity of the sand. And we continue to look a little bit at the littoral transport, so the transport parallel to the coast. Don't worry so much about this equation. It's like it's not directly used in the model, but it's a useful tool to look at a few orders of magnitudes of the impacts here. So the paper is cited, and I will add that reference here before I distribute the presentation. If you put the nonlinear wave theory, the transport, the fall velocity, the reduction of shear stress due to the incidence direction of the waves into one equation, you end up with this rather long expression. And from that we can see what the main input parameters are, and we will explore that a little bit in the next slide. So there's the wave height, and the littoral transport Q, actually it's QL in this equation here, but here I only named it Q, is proportional roughly to the offshore wave height H0 to the power of 3.8. It's inversely proportional to the wave period, 1 over T. Then the proportion of the grain size has a little bit of a complicated expression here with the falling velocity and the grain diameter, so the D50 raised to that expression here. But when you compute this for falling velocity and use the quartz sand with a D50 from 0.1 to 1 millimeter, then you arrive at an expression of D50 raised to the 3.5. So the transport is proportional to D50 raised to the 3.5. On this occasion, let me also recall grain diameters we talk usually in millimeters because of the very small numbers, but equations and models, if not others specified, like this expression, for example, uses SE units. So the D here would have to be converted to meters, so it becomes very small numbers. Just keep that in mind also when you input parameters into the littoral model. Always pay attention to the unit. It's a common mistake to get it here wrong with a factor 1,000. Then the wave incident angle, alpha, we already discussed that a little bit. So rotating that the radiation stress normal direction into the normal shoreline normal direction by the angle alpha causes the shear stresses and thereby the longshore currents and thereby the longshore transport. And the longshore transport is therefore roughly proportional to sinus to the 5/2 and depends on these angle 2 alpha. And then it also depends on the shore face slope. And it's the littoral transport is increasing with steeper slopes. Now we look at that a little bit more in a graphical sense. So the first component here is the wave exposure and the incident angle. First, a little bit of a recall, a few definitions. So we have a coastline. We have a normal to the coastline, which is at a right angle. In this example, north is up, but that of course doesn't have to be the case. So in littoral and coastal morphology, the coastline orientation and normal to the coastline is much more relevant than the north direction. But then of course, offshore wave directions with respect to north, so it has to be that has to be taken care of. And you also need to here pay attention of how exactly the model is how the model definition is, the input model. But the definition that's used in the littoral, in the LitPack, and also throughout those slides is then that the wave direction is offset from that normal coastline with an angle of alpha. So we have the wave front. Here we can see the effect of that it's aligning with the contours. And the angle alpha 0 is again the incidence of angle in deep water. And let's first look at the at this graph and the three curves in the right graph, which is giving us an indication of the littoral drift capacity with the wave height. So in this case, the offshore significant wave height. And we talk about protected shores, so significant wave height less than 1 meter, moderate exposed between 1 and 3, and very exposed above 3. And you can see that as a Q here without any quantities, just as a conceptual, is exponentially increasing with the significant wave height, which we also saw before. It was raised to the 3.8, if I remember correctly. So again, the importance, as I said many times before, the importance of high quality input data is really crucial, because if you, especially here, I mean, where you're looking at where coastline morphology is interesting, and we're concerned with it, we usually in the moderate or exposed areas, right? If it's very protected, there not much is happening, so we're not concerned with that. You have a huge dependency on the wave height, and that means we balance to get the net littoral transport. We will see that in a second. We sort of balancing very large numbers, and if you look at the balancing or look at the difference of very large numbers, a small mistake here can give you very different and wrong results. Like you can get the transport in the wrong direction, etc. So just to keep that in mind. And there is the dependency then on the incident direction is shown here in this graph. So we have the equilibrium orientation here in the center, which would be 0 degree alpha, because then my normal stresses of the wavefront would be already aligned with the normal and normal to coastline and parallel to the coastline, so no shear stresses, so no littoral current and no littoral transport. Means that when I'm aligned, I have no littoral transport. I have yellow, red, and dark red for protected, moderately exposed, and exposed. Independent of the wave height, if I have perfectly aligned waves, there is zero transport. And the same is for minus 90 and 90 degrees, but that's more theoretical cases. I mean, we don't have large waves that are very seldom large waves that are at 90 degrees. And then again, we have the directional spreading. So even if the mean wave direction is taking one of these, there will always be wave components that taking other directions. But anyhow, at minus 90, 0 degrees, and plus 90 degrees of this alpha, the littoral transport is 0, and the maximum is given at 45 degrees. And again, also it becomes obvious that the mean wave direction thereby is an important parameter, and that should be taken into account when, for example, setting up or obtaining or asking someone else to set up a spectral wave model to provide offshore waves conditions, which you are planning to use for a littoral transport model. The directional resolution of the spectral wave model should be fairly fine, for example, 10 degrees, to reduce this error that we're making here as much as possible. While for other applications, 30 degrees directional resolution might be perfectly fine. But here, the mean wave direction is really a governing parameter. And the same, by the way, I can add that now. I forgot to mention that I put a note when we discussed the directional spreading and the reduction of the shear stress. I also mentioned that the directional spreading parameter, which is an output of wave models, is also an important parameter for the littoral transport model. And that is actually, when using third-party wave data, it's not always available. So also keep that in mind. If you have an impact on the wave modeling, keep in mind that you also require the directional spreading parameter. But there was a side note here, which I forgot to mention earlier. My apologies. Here's an example of the transport rates Q with alpha in the columns, and now only concerning one sector. So we go from 5 to 75. We don't go 0 and minus 90. Then you would get the same symmetry. You would get these with a minus. And then for different wave heights. So it's basically No additional information to what we've seen graphically before, but here just some numbers as an example, also again from the Shoreline Management Handbook, but you can also reconstruct that yourself by the end of this course. So as a function of HS and alpha, and here to really end up with concrete numbers, we also of course need to assume a D50, a grain size, and we need to assume a mean wave direction, which in this case is kept constant. I don't know maybe it is shore normal, but it's irrelevant for this observation here. And 20-meter water depth. And we can see huge, and what is the main message here again, at 45 degree, as we already discussed before, we see the maximum, so per wave height, we see the maximum at 45 degrees, and we see quite a decrease at only 15 degree steps away from that maximum direction. And we get also, again, we can see this exponential increase with HS from 350, 3,000, 50,000, 40,000, 100,000, right? So exponential increase here. So again, where we are in this here with my cursor has a huge impact, and we're looking at cubic meters per 24 hours. So if you're modeling 10 years and you look at hourly data, and for each hour you want to figure out what your transport is, and then you add up all these transport rates, again, this adding up large numbers and looking for small differences is really, really sensitive to the wave input data. And we will, I think the plan is that we will be looking at one hands-on example where we can discuss a little bit further what that means for the choice of the positioning of the offshore, of the location of where we extract the offshore wave conditions. We need to take that into consideration as well. Again, that we need to get this input data correct. Then the littoral transport. Last slide on the littoral transport, we said that before it varies with the distance from the shoreline. So here we're now looking at two examples where here we have the shoreline at 0 meter, and then we're going offshore. One for D50 of 2 millimeter, one for D50 of 0.2 millimeter, and one D50 for 0.5 millimeter. And again, for sort of mild, moderate, and severe wave conditions, HS 1, 3, and 5 meters. And we discussed before that the littoral transport, so this is the cross section of the littoral transport, which is parallel to the coast, and the magnitude of that the maximum position of the maximum depends on the position of the breaker line, and the position of the breaker line depends on the hydrodynamic conditions, because waves of different height and period in different water depths break at different positions. In this case, the water level is kept, for this example, the water level is kept constant, and the so-called equilibrium profile, we will also introduce that in a moment, for the D50 and 0 for the two D50s is assumed. So it's a fixed bathymetry, and then these computations are performed. And we can see both a huge dependency on the D50 and a huge dependency again on the wave height. We discussed the wave height before, but let's fix the HS 5 meter and look at these two D50 values, which we often or sometimes might only know at the beach, and we sort of assume that the D50 is constant across the entire shore profile. Then for 0.2 millimeter, considerate or transport becomes, the littoral transport becomes 0 at almost 1,800 meters, so 1.8 kilometer offshore, whereas for the 0.5 millimeter, it becomes 0 at about 700 meters offshore. So you also need to assess for every case, depending on what D50 you have, depending on what your extreme wave heights are, how far offshore do you need to actually go with your cross shore profile in the model? Because in the end, we are interested in the integral of this here, like for most applications. So the integrated, the total littoral transport along the coast. And if you in your LitPack model in this case here of the bold line had only put in a profile to here, you might be missing this offshore part of the littoral transport. So be aware that this can be extending quite far offshore, and actually also in the DHI mic manual, and I assume we will also get to that during the course. It is a common. There is one way of assessing that beforehand, and we will talk about that in a moment. But another quality check is also to simply model with a very long cross-shore profile the sort of most extreme event and look at the results and basically plot this line here and have and ensure that you're covering the entire littoral zone where transport is happening. And like, let's say you have a coastline with a D50 of 0.2 millimeter and a maximum HS of 5 meter in your 10-year historical record, and you want to model these 10 years. And in your first attempt, you put a 3,000 meter bathymetry in, and you get this result. So you only run this extreme event. Then you can quite safely, and let's say it was for the most conservative water level, you could quite safely say, okay, I model out to 2,000 meters as an example. Littoral transport, still longshore transport. There's a so-called, excuse me, 1 second. I apologize. I worked from home today, and the cat was complaining to not get through my office door. Apologies. Littoral drift budget. Still looking at the longshore. So in this rows here, which we will be discussing in a second, the coastline shoreline orientation. Sorry, shoreline orientation is indicated here. We're still looking at the transport parallel with that line, and the net littoral drift is so the difference between the transport in that direction and the transport in that direction. Because if you consider a wave climate like this one here, it's a wave rose, so it's indicating the probability occurrence of waves for certain directions, given by the directions and the polar coordinates, and the wave heights given by the colors, then all these will be causing littoral drift of different magnitudes and in different directions. And there's actually, I might as well already introduce that now. We will iterate that again later in the course of the course. There is 2 ways of modeling this. One would be a time series, like you might have 10 years of these wave conditions, and you just also model 10 years of the littoral drift. Or another way, I said before, if irregular water level and current variations are not dominating your site, you might also all the way look at it in a statistical sense and derive such a scatter table of wave heights and directions and occurrence percentages. So this here I can't now read it off this table, but this let's say this spin here would occur 5% of the time. Then we could also compute the littoral drift for this wave condition, and the result is applied 5% of the time. So it can also be computed in a statistical sense. And then after we have all these individual contributions, be it in a statistical sense or in an hourly resolution or whatever in a time domain sense, we can add it all up, and then the result will be the net littoral drift. So the net littoral drift is a single value with a single associated direction. Either it goes in that direction or it goes in that direction, given for a specified period, of course. If you look at 1 year, you might have it in the one direction, and if you look at the other year, it might be in the other direction. But in a historical sense, let's say over 10 years, you will in the end get one net littoral drift per cross-sectional profile. And there's, for example, there's a little example here to illustrate that a little bit further. So here we have a given like the one that is shown here. So we have a southward littoral drift of 1.1 million cubic meters per year and a northward of 500,000 cubic meters per year. And let's quickly see if we can recognize that here in this wave rows of the wave climate. This is the coastal orientation, the normal to the coast, and clearly the most waves are sort of coming from a northerly direction of that normal with a large occurrence here. And also the highest waves appear to be coming more from north. Like this here, for example, doesn't go to orange and red. So we would expect in such wave climate, we would expect the most transport to go in that direction. So southward transport, 1.1 million, larger than northward transport, 0.5 million cubic meters. And that these sort of steps I also recommend to sort of go through when looking out at outputs from the model, because it's too easy to just get one input parameter wrong. Maybe the mean wave direction was not defined as going to, but as not as coming from, but as going to, etc., etc. So graphical representation of the wave conditions, a quick check of the results, it's always a good idea. And then if we have these two components, southward and northward, we get in this case, we get a net southward littoral drift of 600 cubic meters. And that is, as I said before, that is important for the coastline development, because if there is a gradient in the net littoral drift along the coastline, that will mean deposition or erosion of the beach. Another number is to take the absolute sum of these two. So irrespective of the direction, we add the 1.1 and the 0.5 million cubic meter, and we get the 1.6 billion cubic meters. And this again is important when we look at the backfilling of channels. So let's say you look at a little harbor entrance, and you're not interested in the net sediment that over the course of 10 years passes that harbor channel, but all the sediment that might be moving back and forth will every time partly settle or potentially settle in that harbor entrance or whatever other feature or coastal structure you are analyzing. So important for coastline development, the net transport, important for backfilling in channels and etc., the gross transport. So the nominal sum of these two. And then another important concept is the equilibrium orientation. We looked before at the Q alpha table, so the dependence of the littoral transport on the incident angle alpha, and that is here displayed as a curve. So we have a present coastline in this example here at 280 degrees north. And if we then take the coastal profile and perform LitPack variations by simply saying that this coastal profile has another orientation, so we change the angle alpha, we get different transport rates. And there will be one angle where the transport rates become cross the zero line, so from positive to negative or the other way around. And this location here, where for a single wave, I said if a single wave train is normal to the beach, there will not be any littoral transport. And this is the same concept here, only that is on average. So all the wave trains from all the different directions with all the spreading, etc., on average at the considered position over the considered period of time have a zero net transport. And this is without now going further into this because in the light of time, but the difference of this is a very typical analysis because the difference of the present coastline and where the theoretical orientation of the net zero transport is has a huge impact on what coastal protection measures can have what sort of impact and can they be successful or not. Because if the difference is only very little, one might with coastal structures artificially locally change the coastal orientation a tiny bit to achieve equilibrium profile, and then that might be a very effective measure. If the difference to the present coastline is so huge that cannot be reached, the same measure might only lead to loss of material to offshore. So the equilibrium orientation is definitely a concept that you will be coming across again when analyzing shoreline and coastline morphology. Now the cross-shore transport. So still talking littoral transport. On the first slide, I said there's two main components. One, the littoral transport, parallel to the coast. We discussed in the last few slides. Now the cross-shore transport, so normal to the coast, and that's almost the last section here of my introduction. Varying wave conditions result in varying onshore and offshore transport, and that is so that means that basically the transport of material or sand towards the shoreline and away from the shoreline is a highly dynamic process and changing all the time. And it is to some extent reversible and usually not critical in terms of coastal stability. So coastal stability or coastal instability would be if the cross-shore transport moves sediment permanently away from the point of interest, then it's unstable. But the moving within the littoral zone, offshore and onshore, is a natural process and reversible. So an example here of Palm Beach in Queensland, Australia. These are actually measured coastal profiles. So we have here the bathymetry in meters AHD, which I don't know. It's some Australian height datum, some local vertical datum used here in these measurements. But let's assume somewhere around zero we will have our shoreline. So we actually have a little bit of positive elevation here, which is sort of the dune hinterland. Not the hinterland, sorry, the dune area of the coastal area. And then we are below the water level and going offshore up to 1,000 meters offshore. So zero here will be, zero might be the coastline, not the shoreline in these plots. But anyhow, we have on the 28th of April, this gray record here in the top plot has been recorded prior to a major storm. The data I haven't written down here, but it's irrelevant. And then the black solid line on the 2nd of June has been recorded some days after that storm event. And we can clearly see here that the red area is so the loss of material, because the later record is below the gray record, that some dune material has been lost, and also the offshore profile in the near shore towards the shore has been flattened considerably and there's a bar that had developed here over time. We discussed the undercurrent, which in normal conditions there will be an underflow, which will continuously transport some sediment offshore, and a little bar will develop here. This bar completely disappeared during the storm event, but contrary, there is some material deposited here further offshore. And then the black one is depicted here again, the 2nd of June, and then almost a year later, the blue line. And there we see some sort of very continuous beach profile. And that observation has led to the concept of the equilibrium beach profile. So basically the idea or the observation with some research that there is a time averaged stable beach profile. And that the formulation, an accepted formulation by Dean from 87, is that equilibrium beach profile, the water depth as a function of x, where x is the distance from shore, can be expressed with this exponential formulation a times x to the power of m. And so several investigations like the one presented for Australia around the world, also the Danish North Sea west coast is actually very well monitored historically. And these investigations have revealed that the coastal profile has some average characteristic form, the so-called equilibrium profile. And for M, Dean has suggested something like M to the, so through fitting is something like 0.67. However, in reality, it varies between 0.4 and 0.8. And A is a dimensional steepness parameter with an empirical expression, again fitted to observations depending on the settling velocity. So these theoretical profiles depend on D50, and that's depicted in this plot. So for a given D50, you can get all these theoretical profiles. The limitation you can already see: if you get D50 wrong, you have a wrong profile. If D50 varies from what you might see on the beach to offshore, you have a wrong profile. If you have a geological feature like a clay layer or whatever, which is not non-cohesive but has a large resistance to erosion, you have a wrong profile. So this is only one of the tools, and it can come in handy sometimes when for two things. The one thing is you might have no better bathymetry data available, or you might have a gap between offshore water depth data and inland terrain data. You might use this to fill the gap. I can possibly show an example of that in the hands-on example later in the course. And the second application is you can use this when evaluating beach nourishment measurements. So when you have a given profile, and what happens now if you add sand to that situation, where what gradient and what D50 would that sand material have? So what equilibrium profile will it try to develop towards, and how does that equilibrium profile compare to the actual cross-sectional profile that we have out there? So equilibrium profile, another important concept in the littoral transport assessments. And the last one of these sort of concepts is the so-called closure depth. This equilibrium profile is relevant within the littoral zone, and we heard before that the littoral zone is somewhat similar to the width of the breaker zone, and defined by where the wave break, and it's been defined as it's been found that the exceedance of 12 hours per year significant wave height offshore, where these break is a breaker zone, and there is also an empirical formulation for the so-called closure depth. So it gives you a depth value, and if you then either have bathymetry data or you assume the previously described equilibrium profile, you can then find the distance of that closure depth from shore, and the concept is valid for normal sandy coasts. So if we combine the theoretical equilibrium profile with the theoretical closure depth, so I might just go these 2 slides back. So if we for the D50 have these equilibrium profiles, and for the same D50s compute the closure depths and find where is the closure depth here situated, where's the intersection of the closure depths with my profile, then we get theoretical surf zone width for and here shown again for different wave heights. So for example, HS 3 meter would be the yellow line. I have maybe on the sand a 0.2 millimeter grain size D50. So the surf zone width would be somewhere 500 meters. So that would be a very first indication of how long the cross-shore profiles need to extend offshore to model the entire littoral process. It can be a first impression when assessing to set up a spectral wave model to model offshore conditions whereas high resolution in the wave model required to then later extract wave data. So it's a very handy tool. But again, it's also somewhat a crude expression because the grain size is not constant. There might be other features, etc., etc. So also always check if your cross-sectional profile for your littoral drift computation extends long enough seaward by just simply running a test. We discussed that before, and then you just look at the littoral drift distribution across the profile, and you just check that it reaches 0 for an extreme event within the profile that you model. But this is another tool, very very useful for a first assessment of the job that needs to be done. And then a last thing, the last 2 slides, and then you guys are released from me for today, is maybe a little bit out of context here, but and also not presented like that in the shoreline manual. But I still think it's a useful concept to recall. It's a Shields parameter. When we will come across it sometimes on some occasions in the context of littoral drift, and also in the scientific documentation and user guidelines. It is mentioned. It appears in some governing equations. So just to quickly recall it, it's and also I find it very fascinating actually this example, because it's quite a famous experimental campaign by Shields from 1936. Sorry, and we are now sitting here almost 100 years later, and it's still in offshore engineering and coastal engineering and sediment transport as a general widely applied and accepted concept, which is also used one or the other way in the littoral model formulations. And it simply states that the movement of loose grains, so non-cohesive soil or sand in our case, is given when the shear, it's just a force balance really, when the shear pressure exerted by the water, theta is the shear parameter, is larger than the resistance of the soil, which is the so-called critical parameter. And this here is the original work, was actually done in Berlin by the American scientist Shields. The original graph from his paper, he actually just plotted these sort of experimental observations and came up with this dashed area here, but he didn't even present an expression for this relationship. He just plotted his experimental data. And then later, that was continued by others with more data, and today also implicit explicit formulations for this solid line here exists, which is the critical shears parameter as a function of the Reynolds number, and that's actually what I wrote here, the second part. But let me start at the top. So again, movement of the parameter at the bottom is given if the Shields parameter exceeds the critical shears parameter, and the Shields parameter is an expression depending on the shear stress, the density difference between the grains and the water density, and again the grain diameter. Other formulations often have instead of the shear stress tau, the friction velocity, which is directly related to the shear stress. And so in the exercise of the LitPack modeling, a large part in computing the hydrodynamic conditions is actually also to derive an equivalent or a representative shear stress or friction velocity in the presence of combined waves and currents. And then I have my Shields parameter. And then I need the critical Shields parameter as a function of the Reynolds number, which is friction, which is some ratio of the velocity over the viscosity, and we can use the friction velocity and the grain parameter and get a Reynolds number. But for our applications, we actually always, usually all the way out here in turbulent conditions, where then the critical Shields parameter, which I could read up from this graph, becomes constant anyway. So that's an easy one for usually our applications. And then after we have found the shear stress due to combined waves and currents, we can then see if our Shields parameter is larger than the critical one over here, and if that is given, we will have transport. So that is also a concept that's still used somewhere under the hood of the littoral model package that we are looking at in these days, and the Shields parameter theta you will come across. And with that, I'm actually closing, and the last slide are only the references which I have to update with 2 or 3 references, which will be in the updated version of the slides that will be distributed. So we don't need to look at that too long for now. And yeah, I would just close here and give the word to you, Samir. If there are any immediate questions, we could take them if you want, and otherwise we can do follow-ups, of course, as well.
Okay, thank you, Hendrik, for your nice presentation. Is there any questions from audience?
When you talk about the wave setup, you said that the wave impact level is a summation of flood level and runoff. What about the wave overtopping?
Well, the wave overtopping. I hope I got the entire question correct. If I got it correct, you were probably referring to this slide, possibly, where we looked at the wave setup and different concepts, flooding levels and wave impact levels.
Yes.
And you were asking for the wave overtopping, but the wave overtopping would rather be a concept related to coastal structures such as breakwaters, as we use for ports, for example. So where we extending an artificial structure of a given crest height out into the water, and then we are concerned with if that crest height of that structure is high enough to avoid overtopping sufficiently, or at least limit the overtopping volumes to an acceptable volume. In the context here, where we're looking at littoral transport and the wave conditions near shore, we don't really have an overtopping because this here just continues, right? It becomes the beach, and then it becomes the dune area, and then eventually there's a coastal line. So you kind of, I mean, there might be devastating events. An example could be a tsunami, which I haven't discussed today. So there could be devastating events where you actually have an overtopping of the natural coastline, but usually you don't have that during normal or extreme conditions, that your coastline is overtopped. That is only the case if the natural coastline is not present anymore, and that's of course a situation that you often have in settlements close to the shoreline, that this doesn't naturally continue into the dune area, but we have close to the shoreline revetments. And then we have all of a sudden a structure here, and then we do have overtopping events. But that's not, and that's of course a very relevant coastal engineering topic, but that's nothing that's nothing that we're concerned with in the littoral modeling of littoral transport in a cross-shore profile. Does that, to some extent, answer your questions for now?
What is the recommendation models which assess the overtopping which can be linked with the mine?
Well, there's different. There's empirical models, and you can set up a Mike 3 model. But again, the overtopping is a little bit outside the scope. I would want to say for the littoral transport modeling at this point here, because for now we are concerned with the natural beach and the transport along that, and then if you want to interact, you will be placing structures, and then we need to analyze those structures. We will be dealing a little bit with structures in the coastal evolution module, which is sort of overarching and combining multiple cross-sectional profiles, and there you can also include the effect of local structures in a parameterized way onto the littoral transport. But the other way around, analyzing the wave interaction with structures in a detailed manner to quantify the overtopping volumes, etc. That's not part of the littoral drift modeling. Unless Samir, you have something to add to that statement, or how do you see it?
No, I didn't have something to add here. يعني بقول لك الموضوع ده اوت يعني مش سكوب بتاع الكوريال بروسيس يعني. الاوفر توبينج دايما لو في ستراكشر والميه جت تروح انت بقى ميه نطت من فوق بس ده يعني حاجه لو مش الميه حاجه يعني بالكوريال يعني انت عايز تربط معاه في ايه؟ يعني الميه مثلا غلط وبعد كده يعني تفكير ليه بين الغلط والاوفر توبينج. الران اب والاوفر توبينج ده في فلودنج. Flooding, that is hydrodynamics, which is completely next training session. يعني كنت مش عارف بس هو flooding. Okay.
Well, you might maybe as a last comment, maybe I'm starting to now get a little bit your idea. You might, of course, then come in a situation where maybe the littoral model, as we discussed it here, is not applicable anymore. So if your coastal processes here are so much impacted by a massive structure, maybe even extending into the water, well then that is not a position where you can place a cross-shore profile and where the littoral drift model is applicable. Then you need to choose other analysis and modeling techniques.
Okay. Thank you.
Yeah? Okay.
Please.
Which modeling can calculate the lateral drift quantity of settlement and the net gross one?
Again, please, which model?
Calculate the lateral drift quantity of settlement and the net gross one.
Gross. You speak about gross or the
gross?
Gross. Yeah, please go ahead.
Can you repeat the question for me, please?
which model at mic or LitPack can calculate the net cross settlement budget?
Well, the net cross settlement transport,
Yeah.
that would be, for example, you can obtain that in a post-processing step after your littoral drift profile simulation, where you have an output of the littoral transport rates, and if you sum those up, you will get the net transport. Because the littoral transport that is expressed, well, it's longshore. So if we're looking at a cross-shore profile, it can only be going into the profile or coming out of the profile if you want, looking at the profile. So in your output files, the transport rates will have a plus or a minus, which means upshore, up the coast or down the coast. And if you accumulate those, you will end up with a net, and maybe I just go to the slide. If you just accumulate those, you will end up with a net transport. And if you accumulate the absolute or the normal of that, you will end up with the gross littoral drift. Was that your question and answering your question?
ده 9 عن cross.
الموديل اللي يقدر يحسب لي الكروس كوانتيتي اوف سيتلمنت والديفرنت ده انه موجود بالظبط.
He was talking about the cross, not gross. The sediment normal to the shoreline.
Well, that you could indirectly, you can choose, and probably it will become a bit clearer also when we start to look at hands-on examples. But you can, there are different outputs available, and one output from the cross-shore profile would be a DFS1 file. If you're already familiar with all these mic, I assume there's some familiarity. So if you have a DFS1 profile, so you get the transport rates, the long-shore transport rate in different points along that profile, then the difference of that, the mass balance of that, would also be related to the normal profile, through the normal transport. Because we always assume actually. We assume that there's an indefinite supply of material available for the littoral transport. So there is no limitation. So if there is a gradient across the profile in the littoral transport, then the differences are assumed to just be supplied.
How about the lead prof?
The net
let the littoral the let prof. Let prof module.
Sorry, I don't.
I'm talking about we as you know in the LitPack there are one module called let prof. Which is studying the profile changes.
Yes.
Is it capable to calculate the cross-shore from the net prof sediment transport?
I would have to review that and return with that. Maybe after we also discuss which exact component you're now referring to. You can also call the transport in one point, but usually that's not used in practical applications. So
yes.
And you can also already summed up. You can also output the DFS0, so where you already get the sum of the transports across the profile. Yeah, it depends on the application and what you're interested in.
Okay.
But I suggest a little bit if these also keep these questions then now in mind, and we just make sure that we revisit them again when we get to the different modules in the coming days, just to make sure that I did not now we did not misunderstand our question, and I think it will be easier to look at them in a hands-on manner. I hope that's fine also by you guys.
Yes, it's great. But generally speaking, the 2D sediment transport will calculate it, but it's out of our scope.
Yeah.
There's no ability to do.
No. We will keep this question for next week or the week after. Okay.
I think it's easier in the context of when it comes together in the coastline evolution, right, where we look at the multiple profiles and the. Yeah.
Okay, great. Okay, yes, then huh? Okay, thank you, Hendrik, for this great information and knowledge. And I'm going to complete your session by some practice on using Mic 21.
Yeah.
Great. Okay, thank you.
Are you you continue in English? Probably not. Or...
I will mix.
A mix. Okay. So I might. I was considering to follow to just also be exactly sure of what what you guys achieved, but I suggest we do that in our follow-up meeting, so the two of us make sure that there is no double up of information when we talk after the rest of the session.
No problem. Anyhow, all my presentation in English and will be containing all the information. So the presentation itself, you will be able to catch what I'm going to say now.
Okay, great. Then thank you also to the audience for your interest, and have a good day, and talk to you next week.
Thank you very much, Henry.
Bye.
Bye.
Thank you so much. Thank you so much.
ازاي اجيب النت ما بينهم؟
والتاني
ازاي احسب الكيلو اللي بره الخط الشاطئ؟ ازاي العمليه؟ ازاي اجيب النت ما بين الاتجاهين ما قالش وانا
ما هو قال لك هيفكر فيها كده لمده اسبوع. هو بص العمود هي الكروس النورمال بوزيشن لاين دي مش في النت.
هو كان في تقارير كتير شويه كانوا حاسبينها.
انا ما اعرفش لو وريتني ممكن او يبعتها له هو. شوف هو عامه هيبص على الموضوع. anyhow
بالذات المناطق اللي هو اللي بيبقى فيها ريت كارنت بيبقى عالي او الدروس فيه كارنت بيبقى اعلى من الليترال فدي بتبقى لازم.
جميل. اهلا وسهلا بكم والناس اللي جايين معانا بدايه النهارده. لو امكن بس اخد فيدباك عن يعني شغل حضراتكم الناس اللي موجودين معانا بدايه شغل حضراتكم في الموديلنج ان جنرال وفي مايك يعني بصفه خاصه. فعندنا المهندسه اسماء. اهلا وسهلا بحضرتك يا مهندسه اسماء. حضرتك اشتغلت في الموديلنج ان جنرال؟
انا اشتغلت موديل كتير بس
عملت ايه معلش ايه؟ سبيكترال ويف سيجمنت ترانسبورت اشتغلت بايه؟ ها؟ يعني وعملت ايمج جنريشن وعملت يعني فده جميل. يعني اشتغلت الكابل موديل واشتغلتي هايدروداينامكس. جميل. واشتغلت ليتباك برضه. جميل ممتازه جدا. انت بقى ممتازه جدا. ممتاز.